Hello everyone, my name is Anna Pettoruzzo and welcome back to our machine learning course. Today's lecture is all about the vision transformers and multimodal models. We will start with a quick overview about the vision transformers and we will particularly look at the Python implementation of a VIT from scratch. We will then move towards visualizing the attention waves, and we will finally explore some advanced topics such as multimodal models with vision and text, and also with other modalities. So let's start with a very quick recap about transformer models for text. In the previous lecture, you saw that transformer models usually consist of two parts, an encoder part and a decoder part. The encoder part is responsible to extract some features from the input sequence, while the decoder part is mostly responsible for the output generation. Each part consists of multiple blocks, and in particular in these blocks, we can find the multi-head self-attention layers, normalization layers, and the feed-forward layers. The input sequence is provided in input to the encoder part of the transformer model and is tokenized into vector embeddings. Then a positional encoding is prepended to each of these token embeddings in order to keep track of the position of the token in the original sequence. The decoder layer is finally responsible for generating the output token via a next token prediction objective. We also usually apply a mask self-attention strategy to mask future tokens and make sure that the transformer predicts them without using any information. But what about vision transformer? So in vision transformer, the idea is that we want to provide an input and image and use the transformer model to make classification of this image. So similarly to what we did with text, also for vision transformer, we want to transform an image into a sequence of vectors or token. And then we will use an architecture similar to the one used for text for the classification. But let's look at the different steps of a VIT transformer architecture. So we first have an input image, and we need to divide it into small patches. In particular, here you can see that the input image is divided into 9 patches, and these 9 patches are input in a linear projection that learn and extract some vector embeddings from each of these patches. Then positional encoding is also used to keep track of the position of the vector embeddings in the original image. Plus, we also add an extra learnable class embedding that will be useful for the classification. All this sequence of tokens or vectors is passing input to the encoder part of the transformer model, and then an MLP head is usually used to make the final classification. Let's look now at how we can implement a VIT from scratch in Python. Of course, in Python, there are already some predefined libraries that you can use to implement a VIT. But in this lecture, we would like to show you how we can implement a VIT completely from scratch in order to better understand how the architecture of the model looks like. So let's start with the dataset that we will use for this tutorial. We decided to use a very simple dataset, which is called the Cypher10, and it consists of small resolution color images with a resolution of 32 by 32 pixels. And these images are divided into 10 classes. So our aim is to classify each input image in one of these 10 classes. So you might wonder, why did we use such small resolution images for the classification? And the reason is that VATs are quite expensive to train on large images. And already training a VAT for this Cipher-10 dataset requires more than an hour of train. And that's also the reason why we will provide a checkpoint that you can use to run your model weights and have faster predictions. We saw in the first slides that the first step that we need to do is to patchify the images into smaller patches. To do that, we first need to define the size of each patch that in this specific tutorial was defined equal to 4. And then we can use this reshape method from Python library in order to reshape the inputs images into images that consist of different patches. In particular, if you remember, each image had a size of 32 by 32. And if here we want to divide each image into patches of size 4 by 4, we have in total 8 by 8 patches per image. Then once we have done that, we will move to the implementation of the VAT architecture. And in particular, we will start from the self-attention implementation. So self-attention can be implemented in many different ways, but one of the most common one is to use this scale.product that is represented on the right side of the slides, or also in the equation that you can see there. So to compute the scale.products, we first need to multiply the queries and the keys. We then need to scale these products by dk, which is the square root of the size of the keys or of the queries is the same. We can then apply a mask if we want to, like a causal mask. Then we apply softmax, and finally we multiply the results of the softmax with the value. But let's try to understand a bit better what these query keys and values represent. And in particular, we do that by using an analogy. So you can think about the query as the current tokens question, what am I looking for? While the key is the descriptor for each token that brings some information about what the content of the token actually is. And finally, we have the value, which is the content per se. So if we want to do an analogy, we can, for instance, consider this example. Let's assume that we want to search for more information about the self-attention mechanism in a library. So our query is self-attention mechanism, right? So it can consist of like a question or even some keywords. And then we go to a library and we ask the librarian whether she can retrieve some information for us. And in this library, each book is represented as a key value pair, where the key is the title of the book, while the value is the actual content of the book. And what the librarian does is that it compares our query with the title of the books, so with the keys. It measures the similarities and it ranks the results based on it. She then retrieve the top K books which have high similarity, for instance, with our query, and she then focuses on the content, which is the value of the specific book, to give us an answer that is the answer that we need. Cool. So I hope that with this analogy, the query key and value is a bit more easier to understand now. But again, we saw how to implement self-attention, but what about multi-head attention? Because most of the time using just self-attention is not enough, because we actually want to look at the similarity from different perspectives, so extracting different features. And we can do that by using multiple heads. So in a very simplified way, the idea is that we can first project the inputs to a high dimensional space, and then we reshape the data, stacking all the heads together such that the self-attention process is applied in all of them simultaneously. We can then concatenate the results from all heads before passing the results to a linear layer that projects it back to the original input dimension. So once we have understood how to implement the self-attention and multi-head attention, we can actually have a look at the attention block. So we saw already at the beginning that there are different layers in each encoder parts of the transformer architecture. And the union of all these layers can actually be called attention block. Each attention block consists of a layer normalization, a multi-head attention layer, another layer normalization, and then a small feed-forward layer that, as defined in this case, it consists of a linear layer, a GLU activation function, a dropout to avoid overfitting, another linear layer, and also the final dropout. And if we look at the forward pass, we can see that the input goes into these layers in this order, as I mentioned them. And the one thing that I would like to highlight here is that when we pass our input into the self-attention layer and also the final feed-forward layer, we also need to remember to add the residual connection to it. And then this is it, because actually what we need to do is that we stack a lot of these attention blocks one on top of each other. And this is because at the beginning of the VIT, the tokens will be directly representative of the patches that are retrieved from the input image. But in the deeper attention layers, we will compute attention on tokens that have been modified by preceding layers. And this allows us to actually learn a different type of features that can help with the final classification. So we have already seen how to patchify the inputs. We have seen how to implement the attention block that are at the basics of the transformer encoder architecture. So we just now need to look at the positional embeddings and the MLP hats. So let's first have a look at the positional embeddings or positional encodings that we want to add to the input tokens. So remember that these positional embeddings are simply some vectors that are added to the input tokens in order to keep track of the position of the patches in the original images. So in VIT, this positional encoding is usually implemented as a 2D grid with this equation here. So you can see that the positional embedding can be either a sinusoidal or is a sinusoidal wave and can be implemented either as a sine or a cosine of a certain function. And what is interesting to see is that if we look at different positions in the sequence that are plotted here on the x-axis, and at the hidden dimensionality, meaning like at how the vector look like for each positional embedding at a specific position, we can see actually that they are all different from one another. And you might wonder, for instance, why did the authors of the original paper decided to use these sinusoidal waves instead of simply using integer values from 1 to, I don't know, 1 million, for instance, based on the input tokens that we have? And the reason is that the values could get massive for very long sequences, and the model wouldn't be able to generalize to sequence lengths that it hasn't seen before. right? While sinusoidal have some important characteristic. First of all, each position in the sequence has a unique encoding, as we saw in the previous plots. Then we have that the periodic patterns are repetitive, right? And this ensures that similar position in the original image have actually similar encodings. We have that the sinusoidal are easily differentiable, and this is very good for backpropagation during training. And finally, they allow the model to handle any sequence length. Cool. So now we have everything in place, right? So we can just look at how the forward pass of a VAT is actually implemented. So given an input image X, we first need to preprocess our input, or in other words, patchify it. And then we can do that with this image to patch function that we already saw before, providing in input the image and also the patch size. We then need to input the patches into an input layer, which is just simply like a linear layer for projection. Then we can add the classification token that, as I mentioned at the very beginning, is used for the final classification. And then we also had the positional encoding or positional embeddings to each of the vectors. Finally, we apply the transformer with multiple layers, as you can see here, and then we perform the final classification only by looking at the output in position 0. So this is actually the output that corresponds to the extra learnable class embedding that we have added at the beginning. And that's why I was saying that by adding this token, we can actually retrieve and collect all the information that we extract from the input image. And this information, after being passed towards like an MLP head, can be used to make the final classification. So if we do everything in order, we now have a train function that we can use to just train our model. And here, I provided you a comparison of how ResNet and the VIT perform on these Cypher-10 datasets. You might be seeing something that you are actually not expecting, right? Because if you look at this plot, considering that in the y-axis we have the classification accuracy, we can clearly see that ResNet outperforms the VIT. And this is somehow expected, although ResNet is a simpler architecture than VIT. And this is because ResNet is a CNN-based model, and the inductive biases of CNNs win out if you have very limited data and compute. And that's because in CNN, you know that each pixel, let's say, is looking only at the surrounding pixel, right? So each part of the image only needs to look at the surrounding image part. And for simpler cases like Cypher-10, is much easier to make a prediction just by looking at this. On the other hand, with the VIT, instead, this can also be learned by the model, of course, but it requires much more time and much more data in order to learn this. So the main difference is that in ResNet, this is already encoded in the way in which the convolutional layers actually work because of the receptive fields that you saw in the previous lecture. But in the VIT, this must be learned by the model before actually being able to use this information to make the prediction. Good. So now that we have clear in our minds how a VIT works and how a VIT can be implemented in practice, let's look at how we can visualize what the VIT is actually learning or what is actually looking at. And if you remember, we did something similar with the CNN when we show how to implement GradCam. That was one way to interpret the CNN by looking at which part of the image the CNN is focusing on. And now we want to do something very similar with this transformer, with this VIT architecture. But of course, now we have the attention scores, and we want to find a way to look at them. And looking at a single layer in VIT is not sufficient because, as I said before, different layers extract different features, and they build one on top of each other, and all of them are useful for the final classification. So what we need to do is to compute what is called attention rollouts, meaning that we need to aggregate the attention maps from all the layers to have a comprehensive view of what the transformer is looking at for the final prediction. For instance, if we look at this image of the airplane on the left side of the slide, you can see that a single attention map, for instance, this is the attention map at the very last layer, is not representative of what the model is looking at. But if instead we look at the attention rollout, which is the image on the right side, then we can see that the model is focusing on different parts of the airplane and also on the mountains that we can see in the background. And this then able with this information to make the correct predictions. So let's look at the step on how to compute this attention rollout that we were talking before, and then we will also look at a Python implementation. So the first step is that we want to average the attention map from all the heads of each layer. Because if you remember from before, from some previous slides, we are using now multi-head attention, meaning that at each layer, we don't have a simple self-attention computed on a single head, but we actually have multiple heads. And we want to, since each head compute different features, look at different features, we want actually to aggregate the results from all of them. Then we want to add the identity matrix that is just used to correct for the residual connections. Finally, we compute the actual rollout by multiplying the attention matrices from each layer sequentially. This means that we start from layer 0 with the first attention matrix that we have calculated as step 2. And then for each of the subsequent layers, we multiply the attention matrix with the preceding one. And finally, we look at the attention rollout corresponding to the classification token for a similar reason than the one I was explaining to you before during the prediction. So if we look at the codes, at the Python codes, let's assume that we have already averaged all the attention map from the different sets for each layer. And now we need to do the actual rollouts, average rollout computation. So we start with the rollouts, what we call the variable rollouts, with the attention matrix at the very first layer. Then we iterate through the remaining layer, as you can see here. We added the residual connection, so the identity matrix to each of these attention map. And we multiply the resulting attention residual with the rollouts, which is the attention matrix at the previous steps. And we iterate it for each of the layers in the transformer VIT. Finally, we extracted the attention only of the classification token, which is at the first row. And we discard the attention of the classification token with itself because we don't care about it, but we only care at the attention of the classification token with all the other patch attention. And this is it. As you can see here, if we plot the results, we have that the original image, always from these Cypher10 datasets, is this small horse. And you can see that the VIT, in order to classify this horse, is actually looking at mostly at the leg of the horse and at the center of the horse, and this generating the correct prediction. Cool. So I hope that now it is clear how VIT works. And just to summarize a bit, why do we use VIT? We have seen in this lecture that the VIT are used for classification purposes on image data. But now we want to look at a more advanced scenario, which is, can we actually combine images and text together and have a model, for instance, that predicts some text or predicts some images? And the answer is yes, and we can do that with what are called multimodal models. And there are different types of multimodal models that I highlighted here in the slides. But in this lecture, we will only focus on the highlighted type, which is the multi-to-text model. But let's have a look at them first. So the standard model that we have seen until now is a unimodal model that takes in input some text and outputs some text, or it takes in input an image and outputs a prediction. But if we move one step forward, so one step to the right, so we have what is called a multi-to-text model, where we provide an input both a text and also an image, and we want the model to generate some text. And the one example for this could be, let's assume that you have an image and you want to ask the model to explain this image to you. And the model is just providing you like a clear description and very detailed about what is inside this image, what this image represents, and maybe also the style of the image. Then if we go to the bottom part where there are what they are called image generation model, we have the multi-to-image model, where we provide always an input, a text and an image, but then the model, instead of generating only some text, it actually generates an image. And these are usually generative-based model or diffusion-based models. And finally, we have the multi-to-multi models, where the input is always a combination of text and image, and the output is both the text and the image. Cool. So as I already mentioned before, in this lecture, we will only focus in the multi-to-text model. So, and in particular, we will focus on two different variations, the clip model and the lava model. So let's first look at an example. So we ask our model to tell us something about this image, and we also provide an input the image to the model. And the model is actually able to generate a very detailed and clear description of the input image. But this is an example that I already made before, but there are actually many more use cases that you can think about. For instance, you might consider mathematical reasoning with an image plotting input, or also a web agent with some web page screenshot, or many more. Let's go now into the main approaches. And let's first look at the contrastive language image pre-training model, which is also called the clip in short. This was a very famous and very used model that was proposed by OpenAI, I think in 2021, probably, if not before. And the goal here was to train a model to learn a good image representation. And the idea is that they want to learn this image representation without any label supervision, so without providing in input any ground truths about the input image, but just by input some images and some text that is representative of the given image. And then they use two models. So an image encoder that is defined here as fi of xi. So it takes in input an image and it generates an image representation z of I. And then we have a text encoder, which instead takes in input a text and generates an text representation that is defined here as Z of T. And the main idea of this approach is that we want to force the representation for an image and the corresponding text to be close together, while we force the representation of an image and an unpaired text to be far apart. This is also called the contrastive learning, and is something that was explored quite broadly from the research community. But let's look at an image of how this can happen. So first of all, I want to say that this model was trained on a huge amount of data that consisted of around 400 million pairs of image and text that was collected from the web, and it was never released. So we cannot access to this data. So we have no way to verify exactly how they look like, but of course, there is a quite long description in the text that suggests that we have images like this image of this dog, and then we have some text such as Pepper the Aussie pup. And what happens is that, as I said before, we have a text encoder, which is simply like a transformer model, just using like the encoder parts. And then we have an image encoder, which is the VIT that we talked about before. And what we want to do here is that we want to maximize the diagonal and minimize the elements outside the diagonal. But let me explain a bit better. So let's assume that we have this image of this Aussie pup, or this dog anyway. And then let's assume that this is the image that is defined as I of 1. And then we have its text description that is also defined as T of 1. So what we want to do here is that once we have learned a representation for the text and a representation for the image, we want to maximize the dot products that is in the diagonal, so the dot product between I of 1 and T of 1. But we want to minimize all the other dot products that are outside the diagonal. Or in other words, we want to maximize the dot product of the image and the corresponding text, and minimize the dot product of the image and all the unpaired text. And if we look at how this training loss look like, it has the equation that is represented here on the left side of the slide. So as you can see, we want to, once again, push up, so maximize the dot product of the correct pair, and push down or minimize the dot product of the other pairs. And what's interesting to notice is that, and this is taken from the original paper, in order to compute this, we can simply use a cross entropy loss, as you can see in the bottom parts here, between the logits and the labels. And then we can then simply compute the average between these two. Cool. So you might wonder, okay, you did all this training using contrastive learning, but what's the purpose of this? And the answer is that once our text encoder and image encoder are trained effectively, we can use them as to extract some useful features from the input data and do what is called zero-shot classification. So for instance, now we are at the inference time or at the test time, and we have a data set with different classes, as you can see here, and we can create one very short sentence per class. For instance, a photo of a plane, a photo of a car, and so on and so forth. And then we provide in inputs a completely new image, like this image of a dog. And the model, so the image encoder and the text encoder, are able to extract very good representation from the input image and text, and to classify this image as a dog. So once again, let's have a look at the Python codes. I will not provide you the codes here to implement Clip because we already saw some pseudocode from the original paper before. But what is interesting to notice here is that once again, these models are, the Clip models are available on Hugging Face. So if you just want to test them, just to better understand how they work and whether they perform well on your input data, you can actually just load the models from Hugging Face, as you can see here. And in particular, you need to load both the model and also the processor. And what the processor is doing is that it wraps an image processor that is used, for instance, to pacify the image, add the positional encoding, and prepare the image for the VIT that we saw before in general, and also a text tokenizer that is used instead for pre-processing the text before input it into a text transformer. Then we can load the image from the Coco dataset, for instance, which is a quite famous dataset that you can find online. And for instance, here I just picked an image of 2 giraffes. And then we can define our text descriptor. For instance, here I wanted to classify whether this image is a giraffe or it is a horse. So I picked these two texts, a photo of a giraffe and a photo of a horse. I pre-processed the inputs, both the text and the image. And then I just input these inputs inside our model. And I display the results, and here it is. You can see that in the prediction is that the model is able to classify this image as a photo of a giraffe with 99.9% confidence, which is very, very high. So this model was very famous when it came out, not only for its good performance, because like the image extractor, feature extractor is very good at extracting information from the image and then doing classification, but also because of its innovative way of training a model without label supervision by combining vision and text. And then I want to show you a more recent approach, which is, I believe, from 2023. So this is called the LAVA, which stands for Large Language and Vision Assistant. And again, this is also very famous, and nowadays almost everyone is using this approach for multimodal models. The idea here is that the authors wanted to reuse the pre-trained LLM that were pre-trained only, so pre-trained text transformer to work also with images. So the idea was that we want to project the image tokens that are derived from the different patches, as we saw before, and we want to project them in the same space as the text tokens. And then once we have all these tokens from these two modalities in the same space, we can just provide an input to this sequence to the pre-trained text transformer and generate some text. So this was the main idea, but let's look at the fourth step on how we can do that. So first of all, we need to pre-process our image. And as we saw also with the VIT, one way to do that is that we want to split the image into different patches. And then we want to extract some vector embeddings from each of these patches. And we can do that, for instance, by using a vision encoder like Clip. We don't need, so if you remember before, when we talked about the VIT implementation, we were extracting these vector embeddings by using a linear projection layer. But now that we know about Clip, we know that this is a very good feature extractor for images, so we can just use it, as I showed you before in the Python code, to vectorize each patch inside one representative vector. Then we can project these embeddings with a linear layer, for instance, into the same space as the text embeddings, the text token. And while for the text, we always do the same. So we have the input sentence, we tokenize it, and so we obtain some text tokens. And then we have this long sequence that consists of image token and text token. And then we pass this image inside a text transformer. Sorry, not this image, this sequence inside a text transformer. And then we let the transformer generate the text, such as like the description of this image. And during the training part, actually, we just need to fine-tune our models through two different steps. The first step is that we want to actually train the projection layer from scratch. And this phase is actually very fast because the projection layer is simply one linear layer. So the training doesn't require much computation and is very, very fast. While in the second part, we want to fine tune the projection and the text transformer in order to be able to reach better performance. Cool. And if we look at one example that is reported in the original paper, you can see actually that this lava model performs much better than GPT-4 or Blip2, which is a variation of Flip. So for instance, like they provide an input this strange image to the model, and they ask the model what is unusual about this image. And as you can see, Lava provides a very detailed description of what happens here, such as there is a man ironing clothes on the back of a minivan or van, and so on and so forth. While GPT-4 answer is very short and is not even properly correct because it's saying that the ironing board is attached to the roof of a moving taxi, which is not because it's attached on the back. And for Blip2, which, as I said, is another different model, is even worse because it's simply saying that a man is sitting on the back of a yellow cab. So it's not even realizing that this man is actually trying to iron on the back of the cab. Cool. So far we mostly focus on vision data, which means images, but actually similar models, and in particular this lava-based approach, can be extended also to different modalities. For instance, you probably saw videos like this on the web where robots can do very humanized activities such as loads and unloads the laundry. And you might have wondered how can we implement something like this? So the idea is very similar to what we saw for Lava. So we always have a text transformer that in this case is this Llama 2 model from Meta. And we want to provide in inputs both some images that are captured from the camera that are installed in the robot heads, and also some language instruction. We pre-process the input images as we saw before, and then once we have the vector embeddings, we can pass them to an MLP projector and project these embeddings in the same space as the text embeddings or text token embeddings. And then once we have this very long sequence of image and text tokens, we can input it into the pre-trained language model, so the pre-trained text transformer. And then we can have in output some actions. So instead of outputting like some text that is directly readable from a human, we maybe input the direction of the movement and the angle of the movement and the force that the robot needs to apply. And then we just need to convert it into action that the robot can do. Another example instead is video language model. In this case, I wanted to show you an example from the Quen3 model released pretty recently from the Quen team. And the idea here is always the same. So we have some text tokens here that have been reprocessed and tokenized into an embedding. And then we have a vision encoder that this time is able to take in input both images and also a video. So when you think about a video, actually you need to think about it as a sequence of frames, so a sequence of images. And the only thing that is important to do in addition to images is to keep track of the time step where each frame appears in the video. And that's exactly what they are doing here. So you can see that this purple token represents the time step. For instance, this represents 0 seconds. And this is the token embedding related to the patch of the image at time step 0. And this is like time step, the token represented time step 4. And these are all the tokens of the image that are extracted from the image at this time step. And then we can simply use, as before, a text transformer to output some text, such as picture 1 is an image from a blog. And I also tried to use this model very recently. And so I wanted to show you an example of its performance. So for instance, I provided in input the same video that I showed you before about the robot that is unloading the laundry. And I'm asking the model what is the robotic arm doing in this video. And the answer of this model is that in the video, the robotic arm is performing an autonomous laundry task. It opens the dryer door, reaches inside to grab some clothes one by one and places them into a nearby laundry basket. And then it provides more information about it. So you can see that not only the model is correct about what the robot is doing in the video, but is also able to capture some very small details about what happens in the video. And finally, I want to conclude by showing you also these audio text to text models, where the idea once again is the same as in the Lava-based model. So we have some audio that is tokenized or embedded into some text token space. And then we have an audio stream. So we need to pre-process this audio stream by dividing it into different segments, similar to what we did with the images and patches. And then we input each of these segments into an audio encoder and a projector. And what we have at the end, we also have tokens for each of these segments that are projected in the same space as the text token. We can then provide this sequence with audio and text token in input to our text transformer, that in this case is called here language decoder. And we can output, we can generate some text. And if you think about some use cases example, you might, for instance, think about the question and answer in which you have recorded a lectures or a podcast, and you want to ask a question instead of listening to all the recording. Or for instance, you want to create some minutes from a meeting that you recorded. Or again, you want to extract some information about some speech or the intent or sentiment or emotion from a spoken language. Or again, you want to analyze some music or sounds. And please feel free to think about other use cases because there are so many. So in this lecture, I started by showing you how to implement a VIT and how VIT works. And then we moved toward more advanced model, such as multimodal models, as CLIP and Lava. But then we also saw what happens when we use modalities that are different than image data. And we focus mostly on video, audio, and action data, but there are many more modalities actually that you can think of, such as tabular data, but also time series data, and so on and so forth. The list is very long here. And also remember that in this lecture, we only focus on these multi-to-text multimodal models, but there are more advanced models and different models that not only generate text, but they can also generate images or audio or videos or any other modalities that you can think about. So to conclude this lecture, I wanted to show you also what the current research is looking into in the multimodal model scenario. So until now, we saw with these Lava-based approaches what is called the modular vision language models. And the idea here, as I already said, is that we want to pre-process an image such that the image tokens are mapped in the same space of the text tokens. And then the whole sentence, the whole sequence is provided in input to a pre-trained text transformer. But then people are looking a bit more into what is called native vision language models, where the idea here is that we want to train our transformer model completely from scratch by embedding some vision, so some image information and also some text information. So I don't want to go too much into the details about this, but I really you can check more details in the literature. And I also left here some useful material that you can check in case you are interested. Thank you so much for listening and see you soon.